Hello everyone, this is Faisal Akawi. I would like to go through a complete example of TCP IP and how the messages get transmitted from one machine to another machine within one local area network. For a device to communicate properly on the network, it needs the following four pieces of information. It needs its own IP address. Each machine on a local area network, it requires its own IP address. An IP address can be a private or a public IP address. We will discuss IP addresses, private and public IP addresses in a separate recording, but it requires each device on a local area network, it requires its own IP address. It also requires a subnet mask. A subnet mask in this case would be 255.255.255.0. This is the subnet mask that we will give a specific machine. The purpose of the subnet mask is for a machine when it tries to communicate with a second machine. The only way for a device to know whether the second device it's trying to communicate with on the same network or on a different network is by looking at the subnet mask, which tell it that the first 3 octet is the subnet mask. So if it's trying to communicate with another machine that starts with the same subnet mask, which is 192, for example, .168.5.6, the subnet mask for the second machine will match the same subnet mask of the first machine, and that this way the communication will happen one way, versus if, for example, the 5 was a 6, it will have a different subnet mask, and then it will know that the device that it's trying to communicate with is sitting on a separate network. Therefore, it will send it to the gateway, and that's why each device needs to know its default gateway. A default gateway is nothing more than a router that sits at the edge of the network, and its purpose is if I'm a machine, I'm trying to communicate with a second machine on a separate network, it becomes the responsibility of the gateway to find where is that second machine is sitting, and it will address the communication to the gateway, and the gateway will send it out based on the routing protocols. Routing protocols will also be discussed in a separate recordings on its own. It also needs to know, at bare minimum, the DNS server. Each network, each machine needs to know a DNS. So when you say, I would like to go to www.ibm.com, the machine needs to translate the address from this format into a specific IP address in order to get to that destination. Therefore, it requires a DNS. In the first few labs that you created from this class, you provided all this information. You provided the IP address, you provided the subnet mask address, you provided the gateway, and you provided the DNS. In real life, in practice, practical life, like when you open your laptop, you don't have an IP address or a subnet mask or a DNS. All this information will be given to you through your DHCP server. So at home, when you open your iPad, the iPad will connect to the DHCP server. For those of you who are not tech savvy, so if you have a cable modem, for example, or a switch, it comes with a predefined DHCP. Your device will reach to the DHCP, it requests an IP address, and then the DHCP will provide all the 4 pieces of information needed to your device through the pre-configured DHCP server. In a typical network, a larger network, commercial network, the network manager is the person is responsible for installing, configuring the DHCP and the ranges of IP addresses that can be used. I will use figure 515 from the book to simulate the communication or an example of how TCP IP construct the packets. I will give you an example where client 1 talks to the server on the same local area network. And then I'll give you a separate example on how client 1 would communicate with another client or another server on a separate network. Few points to illustrate before I start the example. One, notice how the figure logically connecting the device or the machines or the PCs directly to the router. We call that a logical representation. But you know by now that the physical representation of how we create a local area network, that we connect these devices to a switch first. Let me clear the screen. So physically, when you created the local area network, whether it's in the lab environment or in real life, the PCs, they are connected to a switch, and the switch is connected to the router. We don't connect devices directly to the routers. One exception you might think of, my access point can be on a separate local area network connected directly to the router. We do that for security purposes. So this way, anybody would connect to the wireless. The only access they have through the router is to the internet. So the question might come to your mind is, why have I been creating or installing and configuring the switch in my local area networks for the past few labs, where we would assign an IP address to the actual switch? As a matter of fact, as you will see in the example shortly, the PCs, when they talk to each other, so if PC1 would like to talk to PC2, whether on the same local area network or on a different local area networks, it will never address the message to the switch. As a matter of fact, the switch is transparent. It takes the message, it passes it through, and as far as PC1 is concerned, the switch does not exist. It will never address the message to the switch. It may address the message to the gateway in case we want to take the message out, or in case trying to communicate with someone outside the network, but it will never address the message to the switch. So again, the question remains, why do I need an IP address for the switch? The answer is, the only reason we give a switch an IP address, that's if someone would like to directly, someone as the network administrator would like directly to communicate with the switch and manage it, update it, send traffics, reroute traffics for administration purposes. But as far as communication, as we will see shortly, the switch is absolutely transparent. That's why in the figure, the PCs are connected directly to the routers and not to the switch. But this is what we call logical, and this is what we call physical. Another important point I want to illustrate is also notice when you look at an IP address, everything within this local area network, if you look at its IP address starts with 128.192.98. The first three are the same for each one of those machines, is exactly the same. That's what we call the network address. So as you see, building A, we refer to it as local area network 1, has the network address 128.192.98.x, which means that every device in this building will begin with that prefix. For the sake of my example, I would refer to this as x.x.x. whatever. I will only provide the last digit. Now, if you look at the second building, which is a separate network, it has a completely separate IP address, 128.192.95.x. I will refer to that as y.y.y.whatever. And each device has its physical address or the MAC address. I will only use, in my example, the last digit. So the first one, whatever that number is, OB, A3, and I will use whatever. I'm only, just for simplicity, I'm only going to use the last digit. Now, this is also important that when you do your project, every device on one local area network, when you do your subnetting, and you'll see subnettings in a separate recordings, they all have to be within the same subnet range. You cannot go to class B or building B and say, I'm going to assign 128.192.98, which is a class from A, .5 into building B. The system will not work this way. So there is an exception to that, which is the VLAN we'll see in future recordings. But as far as what we're doing so far in this class, at this point, each IP address within building B must begin with the same prefix of building B. Also notice that the connection between the routers from this point all the way to that router, to this router, to this router, all this red link, it sits on a separate network. There is a third IP address class, which is in this case 128.192.254.5. So keep that in mind. To illustrate with an example, I have router 1, router 2, and I'm looking at LAN 1, looking at LAN 2. How many different IP addresses do I need? How many different set of IP addresses do I need? How many different, in other words, how many local area networks do you see? If your answer is 2, that is incorrect, because this will be considered one local area network. This will be considered a second local area network. This will be considered a third local area network. So for example, if you would use 128.95.6.0 for this local area network, you would use 128.95.7.0 for this local area network, or the network between the two routers, and you will use a third set of IP addresses. In this case, you would use 128.95.8.0. So I said here 95, but I wrote 99. But it doesn't matter. They're both different IP addresses. This is simply to, I mean, in real life, we don't waste a class B entirely on two two IP addresses, because in this case, I only need 2. In this case, when you use a class B for this network, you're using 2 to the 16, whatever that number is, hosts. That's how many hosts you're wasting using a class B. The reason I'm using a class B is just simply to illustrate the point. These are 3 separate local area networks. Each time you create a link to a router, that becomes a separate network. Remember, the purpose of a router is to separate communication. So each time you add an arm or a link, you create a separate local area network, and it must have a separate set of IP addresses. All right, let's move on and begin our exercise of using an example of how TCP IP is being used. The first example, I will use client 1 would like to talk to the web server of its own organization that it is sitting on the same local area network with known IP addresses, meaning the client knows the destination IP address that it wants to get to. So let's call it client 1, so let's call that client 1, will generate a packet. The packet will have the following information. It will have the source address. It will have a destination address of the two MAC addresses that it wants. So the first MAC address will be A3 because that's the MAC address of the client. It's talking to the web server, and the web server MAC address is F2. It will also add the source IP address where the message is coming from, and we're going to use x.x.x. The client is 130, and it's trying to talk to x.x.x. The IP address for the web server is .53. So that message will leave client, the client. It will go through the switch. I think there's a switch there. The switch, since it's known IP addresses, known MAC addresses, knows exactly where the device is sitting or where the server is sitting. The server will get the message. So this is client to the web server, and then the web will get the message, and it will return back to the server or to the client. The web server will return to the client the following packet. It will add its own MAC address, which is F2. The destination MAC address is A3. Its IP address, which is x.x.x.53, and the destination IP address will be x.x.x.130. Along with the data, in this case, it will be the actual information, whatever the information is. So if you required a web message, that will be inside that message. And this is how the message translates from the client to the web server, and then the web server would respond back with the actual information. This is knowing IP addresses, known the MAC address, everything is known. The next example would be known IP address, unknown MAC address. The second example I want to go through, same subnet, client would like to talk to the web server. I just open it up here in physical logic. This is how it is physically connected. I know the MAC, I know the source, the client knows the IP address of the web server, but it does not know the MAC address. Remember, if you want to communicate on the same local area network, you need the IP address, source and destination. You need the MAC, source and destination. So the question here is, how do you think that the client will obtain the MAC address of the server? How would it know the MAC address? Because when it constructs the message, it needs the source MAC and the destination MAC. But right now, I know the source IP, which is x.x.x.130, and I know I want to talk to x.x.x.53. I know my own MAC, since I'm the one who's sending the message, and my own MAC is A3, but I don't know the destination MAC. How do you think client 1 or the client would obtain the MAC address of the server? Maybe it's a good point to pause the recording and figure the answer out. But here's what really happens. The step 1, client will send an ARP request. Remember ARP request? Address Resolution Protocol. It will do this. Client will say, I am client A3. I am broadcasting a message. It will fill the destination MAC with Fs. My IP address is whatever. Destination IP address, whatever. Whatever I mean, I am 130. I am looking for 53. It will send this message to the switch. The switch looks at the message. It sees it's a broadcast. It will send the message out into every link it's connected to. Then each machine connected to the switch will receive that message. it would look at the broadcast. It says, okay, someone trying to send me a broadcast message. It looks at the IP address. Well, it's not my IP address. I will ignore it. The only one would respond back is the server. The web server will send an ARP response. And the ARP response would look like this. It will say, I am, whatever the MAC address for the web server, which is in this case F2, it will send the message back to A3, the IP address 53, and the destination IP address 130, which is my client. So through the ARP request and the ARP response, the client now knows the MAC address for the destination. So now, once the client knows the MAC address of the destination, it repeats the process by sending the packet that we did in step 1. It will send the it will send the message. It will construct the message with the source, destination, MAC, and IP addresses. The next example I want to address is, what if the client in building A would like to talk to the client or the server in building B? So what if the client in building A would like to talk to the server in building B on a separate network? So the source IP address in this case will be 128.192.98.1. And the destination IP, so this is the source IP of the client in building A. This is the destination server in building B. As soon as the machine client 1 in building A sees that the destination IP address has a different IP address, that means client A, client in the building A, knows that it's trying to communicate with someone on a different network. So what it will do at this point is says, well, I cannot communicate with anybody outside my own local area network. So therefore, I will send my message to the router. And this is how the message begins. The client goes to the gateway. And that's the purpose, again, for a gateway. So the client want to talk to someone else outside. It sends it to the gateway. It would look like this. The source MAC address will be the MAC address of the client. In this case, it will be A3. The destination, since it's sending it to the router, it will be the MAC address of the router on this side, which is, I know I'm scribbling all over it, which is, I believe it is DB. I can't even read it whether it's DB or AB, but keep in mind that if I have a router and I have a connection on this side, a connection on this side, each connection will have a unique MAC address. So if the MAC address of this side is A1, the MAC address of this side will be B1. So it will be two separate MAC addresses and two separate IPs. So this will be x.x.x.1. This will be y.y.y.whatever 1, but it is completely different IP addresses. The IP address of the left cannot be the same as the IP address of the right, nor the MAC addresses. The router will have a separate unique MAC address for each connection. The source IP address in this case will be the client, which is xxx.130. The destination IP address will be YYY.30, which is this, the IP address for the web server in building B. So the source IP is where the message is coming from. Destination IP is the message where it's going, but the MAC address of the client, and it will address the message to the router. Now the router gets this message, so this goes through the switch. The switch says, okay, this is the MAC address for the router. The router gets this message. The Ethernet or layer 2 and the router says, yep, this is me, I am DB. It will take the message, it will strip away the MAC address, it will send the address to the router. The router looks at the address, says, okay, the client, which sits on 128.192.98, which I called it XXX.130, would like to talk to destination, which is 128.192.95.30. Now the router says, well, this is not my address. The router will say, while the message was addressed to me, I was not the final intended person for that message. The message is simply going through me. So the router will pull out its routing table that get populated by any of the routing protocols that we've seen in the separate recordings. There will be a separate recording about routing protocols. And it figures out, it says, well, I have to send it out through that link over here. So this message 1, which goes from the client to the gateway. Now the gateway, at the message leaving the gateway, the following will happen. So it will create the following connection. Now, one thing you need to keep in mind that the source IP address, which is the 130, destination IP address, which is the .30, does not change anywhere. So the message right now at this point, let's call that point 2, but the source MAC address, the destination MAC address will change. Since the message, the router on this edge of building A want to send it to the router and at the edge of building B, it will leave the link on this side. It will replace its MAC address. So the source MAC address in this case will be BB, where BB is this number right here. The destination MAC address will be AF, which is this MAC address on this side. The message gets, so this goes, let's call this router A. This is router B. So this is router B, gets this message. Router B says, okay, 130 trying to talk to .30. It knows that .30 within its network. So let's call this point 3. At point 3, the router will do this. Again, the source IP will stay the same. Destination IP will stay the same. So this will stay 130. This will stay 30, but it will replace the MAC address. So the MAC address leaving this NIC over here, this link over here, will be B4. Destination MAC address will be the MAC address of the server, which is A0. The web server in building B gets this message, and it repeats the process by sending the message all the way back to router A, and then router A will send it to client A. To illustrate the point one more time in much shorter talk, let's take a look at this network where I have PC1 and local area network 1 would like to talk to PC2 and local area network 2. The IP addresses, as you notice over here, there is one IP address range, which is 1.1.1.2. This point is 1.1.1.1. I'm going to abbreviate the MAC address to A1, A2, B1, B2, C1 and C2. So let's say PC1 want to talk to PC2. It knows this is the source IP, this is the destination IP. Notice that everywhere in this link, the source destination doesn't change of the IP address. The source MAC address is A1. It sent it to A2. The reason it sent it to A2 because the PC1 knows that it's trying to communicate with someone outside its network. The subnet mask for those two IP addresses are not the same, indicating they are sitting in two subnets. So it will address the message to router 1. Router 1 gets the message since it has its own MAC address, but when examine the destination IP address, it knows that it's not addressed for R1, rather than it's going through R1. It pulls its routing table. Routing table says go through this link. Anywhere in the link labeled here blue, colored blue, the message would look like this. The source destination IP address does not change until it gets to the destination. The only thing that router 1 will do, it will say the source MAC address now is going to be B1, the destination is B2. Same process happen. Router 2 gets the message because it's addressed to its own MAC address, but it sees that the destination is not intended for this router because the address for this router is 2.2.2, but the destination is 3.3.3. R2 pull up its routing table, whatever it's using internally over here. Maybe it's using OSPF. We'll see OSPF in the separate recordings. OSPF will say, well, if you want to get to this particular IP address, send it down that path, and source destination remains the same. The router 2 will replace the MAC address. It will say now it's coming out of C1 and it's destined for C2. So Ethernet, it's locally matters through hop. Every time you go through a hop, the MAC address will change, but the source destination IP address stays the same, and the same process gets repeated to respond back to PC1. The next few slides, it simply summarizes what I just talked about in detail. TCP layers, the host computer, how does it gets the message, and the purpose of the gateway and the routers. This is a complete illustration of what really happened when a client in building A want to talk to a client in building B on a separate network. Whether when you open your browser, you say webserver.com, whatever the address is. At the application layer, it adds the HTTP. It sends it to the transport layer. The transport layer will add the TCP, and it will do everything we've talked about the TCP. It will take the message, it will segment it if it's larger than 1500. It will establish communication with client B. It moves it down to the IP address, and the network layer, the router, will add the address for the destination. We'll talk about IP addresses in a separate recordings. Then it sends it down to the Ethernet. Ethernet will add its own overhead to it. And then let's presume that we're talking, since we are a computer, in this case connected, a PC connected to a router, well, let's presume that it is digital to digital. There's no analog here. Each one of these bits will be changed into ones and zeros. So this will be like 1, 1, 1, 0, 1, 0, 0, 1, 1, etc. That will be changed to it. The message will go to the gateway of building A, simply because the machine and building A determined that it's trying to talk to someone else and outside. It will receive, the first thing the gateway will receive is the actual message. This is the physical layer. It will send it up to the network, into the network, or the network layer on the switch, on the router. Since it's addressed to it through the Ethernet, it will open it, but it will determine that the destination IP address is on a separate building. So what the router will do, it will reconstruct the message. It will change the Ethernet, puts it on the line, and etc. The message will go to the second router in building B, or the gateway in building B. Same process gets repeated, and the gateway of building B will send it to the actual client. The client receives the message, it opens the Ethernet, it opens the IP. The server on building B knows that it is its Ethernet, it is its IP. Then it will strip away the TCP, send it to the server, and then the process will repeat itself going back. Thank you, and that's all what I have for you in this recording. This is Faisal Akawi signing out.